Rightio. Seems like we've lost connectivity again. 444404. All right. Okay. So, ladies, no gentlemen, welcome to the fourth workshop. Today, what I want to try and achieve is to go through the homework I gave you on the standard chemical reactions, and then I want to do concentration and maybe dilution, and that's it. Okay. I know you guys have got a math test tomorrow, so I'm going to try and give you some extra time. Right, so formation of salts by means of chemical reactions. We looked at four basic types of reactions. We've got an acid. Let me maybe just recap. Right, we have an acid plus a metal produces a salt. And remember, when we talk about a salt is basically consists of a metal ion, all right? A metal ion, which is normally positive, will be positive, and a non-metal ion, which is negative. And a metal ion and a non-metal ion together form a salt, right? The salt comes from the fact that the hydrogen in the acid gets displaced and replaced with the metal in the acid, forming the salt. And in doing that, it forms hydrogen gas. Okay, so that is the one template reaction. There is an exception to the rule where we took copper and nitric acid, and then it produced that not stinky, it was a very pungent, it was a strong smell. It was almost like a chlorine smell. It was a nitrogen dioxide, that reddish brownish gas. It's an exception to the rule. Then we had that if you have an acid plus an hydroxide, a metal hydroxide, then it's going to produce a salt plus water. All right, so the salt in this case would be M plus, and there would be OH minus. All right, because the hydroxide will give you the OH minus. Okay, I just want to check here. No, that is wrong, Mr. Duffield. That is actually wrong. Sorry. It's going to be the non-metal ion will still be from the acid. The hydroxide will contribute to the water. My bad. Okay. All right, that's an acid plus a metal hydroxide. Please remember that a metal hydroxide is also known as an alkali or a base. So when you have an acid plus a base, it produces salt plus water. So that was the other one that we looked at. Then there is an alternative to that, is when you've got an acid plus a metal oxide, and that produces salt plus water. Right? And the metal oxide is a base. Right, so these two are basically the same thing. That's an acid plus a base produces salt plus water. We will look at what we call titrations next week, right? Which are also known as, these are known as neutralization reactions. I use RxNS for shorthand for reactions. So these are what we call neutralization reactions. An acid is neutralized by a base to produce a salt plus water. Okay, then we looked at an acid plus a metal carbonate. That produces a salt. It produces carbon dioxide gas and produces water as a liquid. Right? There is an alternative where you're working with a metal hydrogen carbonate, which does the same thing. a metal hydrogen carbonate. Hydrogen carbonate is also known as a bicarbonate. Okay, so sodium bicarbonate or sodium hydrogen carbonate would also be it's kind of a base. It is a base. Okay, these are weak bases. So it's kind of an acid plus a base, produces salt plus water, but because it's a carbonate, it produces carbon dioxide as well. But these are the fourth type of reaction. And I proved to you last week that when you react zinc plus hydrochloric acid, you get hydrogen. Remember, we did the POP test. We collected the gas and we did a POP test. Remember, we haven't done these yet. We will still do these. An acid plus a metal carbonate. Remember, we produced carbon dioxide. We tested it by bubbling the gas through lime water. If you weren't here, then please just go and look at the video. I've recorded it, put it on the classroom. Right, so are you ready? Are you steady? Let's go. Okay. So, homework. Nitric acid and magnesium. Nitric acid, HNO3 plus magnesium produces magnesium NO3 2 plus hydrogen gas. You need 2 of those. Bang, done. Are you happy with that? You're going to mark it. So what are we working with here? We're working here with an acid plus a metal, which is not copper, is a salt plus water. That is the template. I think this was 1B. 1B. 1C is sulfuric acid, which is H2SO4 plus aluminium. All right, this is going to produce aluminium SO4 3 2 plus H2O. Not 2 of those, 3 of those, and 2 aluminium, and 3 H2. Let's just check it. 6 hydrogen, 6 hydrogen. 3 sulfates, 3 sulfates. Need 2 aluminiums. Bang, 2 aluminiums, 2 aluminiums. As a matter of fact, you need 4 aluminiums. You need 4 aluminiums because this is sulfate is 2, so you drop and swap. Al2 SO4 3, so you need 4 aluminiums. You need 6 hydrogens. You need 3 sulfates, 4 aluminiums, and that's balanced.
Sorry, in the formula you wrote at the top, wouldn't that be hydrogen instead of water?
Yeah, it's definitely hydrogen. It's not. Ah, my word. Sorry, it's absolutely hydrogen gas. My apologies. All right, old age is a terrible thing. An acid plus a metal produces salt plus hydrogen gas, not water. As you note, I put in the hydrogen. Thank you, Isabella. Thank you for correcting me. I apologize. Are we okay with the balancing? I'm not explaining it. I'm putting it out there. Anyone need me to explain it? Here's the trick. Aluminium is 3 plus, sulfate is minus 2. So it's Al2 and SO4 3. Okay, cool. Let's go to the next one. Next one, I gave you hydrochloric acid and calcium hydroxide. Notice this is an acid plus a base produces salt and water. So we're dealing hydrochloric acid and calcium hydroxide. Hydrochloric acid and calcium hydroxide. So let's take a look at 2 on calcium hydroxide. Okay. HCl and calcium hydroxide. Okay. So we've got an acid plus a base. It's going to produce a salt. The calcium is going to replace the hydrogen. So that's going to be CaCl. But Ca is plus 2 and chlorine is 1 minus. This is going to be CaCl2, right? And this is going to produce water, which is H2O. An acid plus a base produces a salt plus water. Now we need to balance. Can you see you've got 2 chlorines there? Which means we need 2 chlorines there. So it's going to be 2 HCl. Right? We have 1 calcium, 1 calcium. How many hydrogens do we have? We have 2 hydrogens, and we have another 2, which makes it 4. So we need a 2 there. So if we check, we've got 2 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens, 1 calcium, 1 calcium, 2 chlorines, we're done. Okay, so that was 2A, 2A. 2B. We have, so we've done that, nitric acid and magnesium hydroxide. Nitric acid and magnesium hydroxide, MgOH2. Right. We have an acid plus a base produces salt plus water. Okay. Let me just quickly stay in the call. Right. So now, the salt is going to be magnesium NO3 2. Mg plus 2, NO3 minus 1, drop and swap, right, and it produces water. H2O. Right. 2 hydrogens, right. Let's go to the nitrates. I like to look at the polyatomics. The polyatomics, I need 2 NO3, I've got 1 NO3, so I'm going to put a 2 in the front of HNO3. Right, I've got 2 hydrogens plus 2 hydrogens is 2, got to be 4 hydrogens, so that's got to be 2. We've got magnesium, we've got 4 hydrogens, 2 oxygens, is balanced. Are we happy with that? Okay. Remember hydroxide, OH minus, Mg plus 2, drop swap, Mg1, OH2. Okay. Number 3. 3A, hydrochloric acid and calcium oxide. Once again, we're looking at an acid plus a base produces salt and water. But now our base is going to be a metal oxide and not a metal hydroxide. But it's still going to produce salt plus water. So we're looking at 3A, hydrochloric acid and calcium oxide. 3A, hydrochloric acid and calcium oxide, CaO. Right. Calcium is plus 2, oxygen is minus 2, so it's CaO. Right, so we're going to land up with calcium chloride, which is going to be CaCl2. Ca is plus 2, chlorine is minus 1, chloride is minus 1, drop and swap. Right, now we've got water, H2O. Now, we've got 2 chlorines there, so we need 2 here, so I'm going to put a 2 in front of the HCl. All right. I think it's balanced. 2 hydrogens, 1 oxygen, 1 oxygen. 2 chlorines, 1 calcium, 1 calcium. Okay, I'm going to say this. This is not the main focus of what we do. Eh? If you get a balanced equation, it will be separate from a stoichiometric calculation. I spoke to Dr. Rousseau and he said that the only time we can ask you in tests and internal exams, they can ask you to produce the equation for a titration. They give you the acid and the base. Okay, we can. But a lot of the time, 9 times out of 10, we actually give you the equation. Okay, for the reasons I explained last time. All right. 3B. Sulfuric acid and aluminium oxide. Sulfuric acid, H2SO4, aluminium oxide, Al hydroxide, OH. So it's Al, the 3 goes there, OH1, so it's Al, OH3. No, sorry, aluminium oxide, not hydroxide, aluminium oxide, my bad. It's going to be 3, 2. 2, O minus 2, 2 goes on there, Al plus 3, 3 goes there, Al2O3, aluminium oxide. Right, plus, this is going to give us aluminium sulfate, SO4, 3, aluminium 2. SO4 is to the negative 2, Al plus 3, 3, 2, okay, plus water. Okay. So let's go to the sulfate. We've got, I like the polyatomics. If you see the polyatomic hasn't been broken up, then the polyatomic helps you with balancing. SO4, 3, we've only got 1 there. So there needs to be 3 sulfuric acid. Okay. We've got 6 hydrogens and 2, so we need to multiply by 3 here. So now it's 6 hydrogens, 6 hydrogens. We've got 2 aluminiums, 3 sulfates, 3 oxygens, kabang, balanced. How are we doing? We all right? Okay, excellent. Cool. We'll post this. Right, let's go to 4. 4 is an acid plus a carbonate or a hydrogen carbonate, obviously a metal carbonate or metal hydrogen carbonate because we produce salt water and carbon dioxide. So 4A, we've got hydrochloric acid and calcium carbonate. Hydrochloric acid and calcium carbonate. Okay. Hydrochloric acid, HCl, and calcium carbonate. Calcium is plus 2, carbonate is minus 2, so it's CaCO3. All right, so we'll end up with calcium, Cl2, plus CO2, plus H2O. Why do we know that? Because this is a metal carbonate plus an acid. Produces a salt, plus carbon dioxide gas, plus water. Right, looking here now, let's check our formulae. Plus 2, minus 2, plus 2, minus 1, so it's CaCl2, CO2, H2O. Right, let's take a look there. I've got 2 chlorines here. I need 2 chlorines there, so I'm going to times by 2. Okay. I have 1 calcium, 1 calcium. I have 2 hydrogens, 2 chlorines. 2 hydrogens, 2 chlorines. I've got CO2, 1 carbon, 1 carbon. O3, O2 plus 1 is O3. Balanced. Okay. 4B, nitric acid and magnesium hydrogen carbonate. Nitric acid and magnesium hydrogen carbonate. So 4B, nitric acid is HNO3, magnesium hydrogen carbonate. Now, just be careful. Carbonate is CO3 minus 2. Hydrogen carbonate is HCO3 minus 1. You've added a hydrogen ion. Okay, so this needs to be 2 because the HCO3 is minus 1. Okay, just think about that. You got a CO3 minus 2 and you add a hydrogen plus 1, you're going to land up with an HCO3. Minus 2 plus 1 is minus 1.
So hydrogen carbonate is actually a substance.
It's a polyatomic ion. Yeah. So if you go and you look at baking soda, have you heard of sodium bicarbonate? Have you heard of sodium bicarbonate? Bicarbonate of soda. All right. That is a hydrogen carbonate. Okay. Oh, baking soda produces carbon dioxide. Used for raising cakes and breads and that sort of thing. Okay. So what do we got here? Rightio. So now we're going to go, okay, so we're going to have salt, MgNO3, MgNO3 2. MgNO3 2, Mg is plus 2, NO3 is minus 1, plus CO2 plus H2O. So let's see how this works out. Once again, I start at the polyatomic. 2 NO3s, I've only got 1 there, so I'm going to multiply by 2. All right, magnesium, I've got 2 NO3s, 2 H's, 2 H's. 1 magnesium, 1 magnesium. But now I must be careful. H's, I've actually got 4. Look here. 2 hydrogens, 2 times 1 is 2, so that's 4. So I actually need to have 2 waters because I need 2 times 2 is 4. So I've got 2 hydrogens is 4 hydrogens. All right, which means now if I look at NO3s are on their own, look at the oxygens. 2 times 3 is 6. So I am going to need, and you see I've got 2 carbons here. I'm going to need 2 CO2s plus 2 CO2s. Why? Because I've got 2 carbons. You add 1, so it's 2. 2 times 2 is 4 plus 2 oxygens is 6. 2 times 3 is 6. 6 oxygens. Balance. Okay. Tricky. Are we okay? Cool. All right. Excellent. Fantastic. Right. Can I go on? Okay. Okay. No. Yeah. So what I want to talk about now is concentration. I want to talk about concentration of acids and bases. Concentration of acids and bases. So just a bit of reflecting on stoichiometry, okay? So remember, concentration is the number of moles of solute over the volume of the solution. Okay, so we have a formula triangle. Concentration is N solute over V solution. Okay, now, this is measured in mole. This is measured in cubic decimeters or liters. Same thing. Okay, 1 cubic decimeter is 1 liter. So concentration is measured in mole per cubic decimeter cubed. Mole times decimeter to the -3. Mole divided by liter, or mole times liter to the -1. Or, drum roll, are you waiting for it? Big N. Big N is the unit of molarity, which is fancy for concentration. So in actual fact, all of these are M. But wait a minute, but M, sir, M means molar mass. No, this is M as a unit. M as a quantity is molar mass. Okay, so now we've also worked in stoichiometry. We've worked with the fact that N is M over molar mass. So here we're working in grams, here we're working in grams per mole, and so here we work in mole. Okay, so let's just be very clear about what these different things mean. This is molar mass as a unit. This little m is the sample mass. This N is the number of moles. All right. V is volume. C is concentration. Okay. Now, if I take this and I substitute it into there, got your attention, then I get a very cool equation formula. C equals M over big M V. And you know what? It's on your formula sheet. So that these two combined give you that. Remember this, what this is N equals M over big M.
So the concentration can be displayed as either moles per decimeters cubed or as big M. As the
Yes. All right. Okay, so cool. We okay with that? All right. So what is a standard solution? It's a solution that we know the concentration of. Okay. It's a solution that we know the concentration of. Do you have a periodic table here? Do you need? Who needs a periodic table? That's one of the possible. Yeah. Yeah, the biggest one.
Which calendar do you need one? No, but like one to take home when doing homework.
He's a genius. He's got it in his mind, in his brain.
And there's also one of
In 31 years of teaching, I've only ever had one child that knew the periodic table off by heart. Henry Thackeray. He won the National Maths Olympiad when he was 15.
Okay, well, there we go.
He got his PhD in number theory at Princeton when he was 24. We tested him. All glasses, very English little dude. And we tested him. We asked him to take his glasses off and turn his back to the big periodic table we had. And everyone stood around him and said, "Okay, Henry, can you please tell us what is the relative atomic mass of hydrogen?" Oh, that's easy. So 1.00797. Nah, Henry, that is too easy. Henry, what is the relative atomic mass of arsenic? 74,922. And my colleague who was teaching there was a big strapping professional rugby player by the name of Eben. And he said, no, don't know, Henry, that can't be true. And he said, Henry, in his Afrikaans accent, he said, Henry, what is the relative atomic mass of rubidium? He said, 85.4. So he said, don't know, Henry, you're brilliant, you understand it. Eben went on to Captain Otago in New Zealand. He was a professional rugby player and math teacher. He was an interesting guy, but we tested Henry, and Henry knew the periodic table. And he also knew pi to 1,000 decimal places. Anyway. Okay, so let's go. Let's look at the definition of a standard solution. A standard solution is a solution that has a known concentration. Okay. So we're going to deal with acids and we're going to deal with bases. Okay. Standard solution is a solution that has a known concentration. Good. So first things first, let's start off with, we're going to look at, and I also want to just mention to you that we can also use square brackets to denote concentration. And when we do that, inside the square brackets is normally AQ, because whatever we're looking at the concentration of is a solution. The other thing I do want to mention to you is we make an assumption, which is a good enough assumption. We make an assumption that the volume of the solvent equals the volume of the solution. Because often we will give you the volume of the solution of the solvent. So, for instance, we'll give you 500 milliliters of water, and we assume, by doing this, we assume perfect dissolution, perfect dissolving. So, in other words, there isn't a little bit of saturation, there isn't a bit of solute that is undissolved that displaces the solution upwards. Okay. All right, are we ready? Let's look at an example. Calculate the concentration of sodium hydroxide solution when when 150 grams of sodium hydroxide is dissolved in 255 milliliters of water. Calculate the concentration of sodium hydroxide solution when 150 grams of sodium hydroxide is dissolved in 255 milliliters of water. What is the formula for sodium hydroxide?
Is it NaOH?
NaOH. Okay, so it's very important that you know what the formula for sodium hydroxide is, right? So sodium is in group 1. So we have sodium plus 1, and hydroxide is OH minus 1. So this means that the molecular formula is sodium hydroxide. Okay. So therefore, what is the molar mass of sodium hydroxide? Sodium is 23, oxygen is 16, and hydrogen is 1. So this is going to give us 40 grams per, 40 grams, eh? 40 grams per mole. 40 grams per mole. This is a molar mass. 23 plus 1 is 24, plus 6 is 30, plus 10 is 40. Okay. We okay with that? Right. Now, we are told that the mass of the sample is 150 grams. Right, so that's the mass of the sample. So therefore, we could work out that the number of moles is the mass divided by the molar mass. Okay, so that's going to give us 40 grams per mole. Mass is 150 grams divided by the molar mass, which is 40 grams per mole. I'm purposely using different forms of the units so that you get familiar with them. All right, and so when we work that out, yeah, here we go. We're going to get that that is 150. 150 divided by 40, and that gives us 3,75 mole of sodium hydroxide formula units, because it's not molecules, eh? Right, now let's take a look at the concentration. So the concentration of sodium hydroxide solution, and I'm purposefully writing it like this so that you get used to it, that is going to equal the mass, the number of moles over the volume of the solution. Right? So that's going to be the number of moles is 3,75 mole, and the volume of the solution, we're told that it was dissolved into 250 milliliters of water. So the water is the solvent, so we're going to assume perfect dissolving. So 255 moles, well, 255 moles is the same as 255 over 1,000 liters, because 250 divided by 1,000, because 1 liter is 1,000 milliliters, which is 0.255 liters. But we can also look at it a different way. This is 255 cubic centimeters, and we need to divide by 1,000 to get it to be 0.255 cubic decimeters. Are you okay with that? All right. So therefore, the volume is 0.255 cubic decimeters. So therefore, the concentration of the sodium hydroxide NaOH, aqueous, which we could also have called little c, and we could have said NaOH, is going to equal 3,75 divided by 0.255. And that would have given us 14,706 mole per cubic decimeter cubed. Can you see we've got the mole divided by decimeter cubed, but we could have also said this is 14,706 big M.
So did you have to do it that long way, or could you just use the short?
So you definitely can use in this question, you could have done the straight shorter way. But I wanted to show you the two steps, okay? I wanted to show you step one. It's a good question, Tamlin. That's step one, and that is step two. Step one and step two. Okay. All right, but we could have done it quicker. We could have done it the following way. We could have said, okay, we can go the short method. The short method would have been, all right, we just do it like this. We say, okay, concentration is M over big MV. It was how many grams? It was 150 grams. It is 40 grams per mole. And it was 0.255 cubic decimeters. And that would have given us 14,706 mole per cubic decimeter cubed. You could have done it like that. I'm going to work it out straight. 150 divided by bracket, 40 times 0.255 close bracket, 14,706. QED, quite easily done. Okay. All right. Now, okay. Concentrations are important. I promise you I'm not going to go all the way up to 4 o'clock. Okay, so they're important. What I want to do now is I want to do a dilution problem. Okay, a dilution problem, and then I'm done. Okay, so what I want to do is I want to do dilution. So dilute implies to decrease the concentration of a solution by adding solvent. Decrease the concentration. The square bracket stands for concentration. Okay, so let's look at an example. Okay. A 300 milliliter 0.5 mole HCl solution, okay, needs to be diluted to a 0.15 mole solution of HCl. Here's the key. How much water must be added? Now, these questions pop up in exam questions. All right. Now, they can be quite intimidating if you haven't seen them before. All right. But I want to show you something. I don't want to just give you a formula. There is a formula, but I don't just want to give you a formula. I want you to understand the concept. Okay. All right. So we have initially, we have a beaker, and in this beaker, all right, we have got it's a big beaker. We have got 300 milliliters. We have 300 milliliters All right, initially, we have 300 milliliters of a solution that is a concentration. The concentration is 0.5 mole per cubic decimeter cubed. So in this solution, all right, you have a certain amount of mole of HCl. So the number of moles of HCl initially, we do not know. But we do know the concentration and we do know the amount that we have. So my first thing I want you to do is work out how many moles of HCl are in that solution. Do you agree? Okay. So in the initial solution, all right, we have 0.15 moles of HCl. Now this undergoes a process of dilution, which implies adding water. Okay, so what we do is we take let me see if I can draw it accurately. Right. And now we add a certain amount of water. Volume added. This is the volume added. All right. And I'm going to call it delta V because that's the volume change. Yes.
Do you end up doing it like the same sort of equation, but you say that the volume is equal to V initial plus delta V?
Yes, it is. So now here's the crux. We want this to have a concentration of 0.15 mole. All right, that is the desired concentration. This is the desired concentration. This is why we're diluting it. All right, so we go, okay, all right, so we know that concentration, we know that concentration is number of moles divided by volume. We know that, hey? All right, cool. The concentration we know is 0.15 mole per cubic decimeter cubed. We get it from there. Tell me, when you add water, do you change the number of moles of solute? It's still 0.15 mole of HCl over the final volume. Because concentration is number of moles over volume of solution. Okay? So now we're going to get to the final volume of the solution. No. Oh, in this case, it actually is going to be 1, just so happens. It is going to be 1, okay? Not always 1, but in this case, so V final is going to be 0.1. It's just purely fluke that it's 1, right? Is 0.15 mole over 0.15 mole per cubic decimeter cubed. So we've switched these around. So V final happens to be 1 cubic decimeter. So your final solution is going to be 1 cubic decimeter. But is that how much water needed to be added? That minus the initial volume. So the amount of water that needed to be added, delta V, is V final minus V initial. And delta V is going to be 1 cubic decimeter cubed minus 0.3 cubic decimeters cubed, which is going to give us 0.7 cubic decimeters. This implies 700 milliliters of H2O needed to be added. Okay. Does that make sense? Now I'm going to give you the recipe. If you firstly understand the concept, then I'll give you the recipe. Okay, are you ready? It's a very nice recipe. The dilution equation. Everyone got it? I'm going to post it. The dilution equation. C initial, V initial equals the number of moles of solute. You agree?
Does dilution decrease the concentration?
Yes, because you're adding solvent. Is going to equal C final, V final, where these are the solution volumes. So here's your formula. C initial, V initial equals C final, V final. And V added equals V final minus V initial. There's your dilution equation. Have a wonderful afternoon. I will, when I post the notes in the recording, I will post a few questions for you to do for next week. Study hard for your mathematics test. May the force be with you.